Assalamu alaikum, my dear students. Good morning. Today we will study another important organic reduction reaction that is famous for its name, uh, that is known as Birch reduction. Now, who was Birch? Birch was the Arthur Birch was Australian chemist. So he invented this reduction reaction that is known as Birch reduction. What is this about? The Birch reduction is actually the conversion of, it involves the partial reduction of aromatic compounds into 1,4-diene compounds. Birch reduction is the conversion of aromatic compounds into 1,4-diene compounds upon partial reduction. It involves the conversion of alkynes, not terminal alkynes. It involves the conversion of alkynes, not terminal alkynes, into trans alkene. It reduces the alpha beta unsaturated ketones. It reduces the conjugated dienes. In your previous classes, you might have learned the Birch reduction, but you will have a very brief idea about the Birch reduction. Today, we will try to learn the comprehensive knowledge about the Birch reduction. So basically, without reading this again, I will describe in the form of structures. You see, this is an example of an aromatic system. What is the name of this compound? This very famous compound called naphthalene. So upon reduction with birch, birch reduction, it changes into a diene system. So I'm writing here a specific example of aromatic system. This is a a very small example of, there are different classes of aromatic compounds. They might have pyrrole system, pyridines, fused aromatic rings, isolated aromatic rings, biphenyl systems, all the aromatic compound. I'm talking about all aromatic uh, organic compounds. So they undergoes the Birch reduction. They undergoes only partial reduction and they changes into 1,4-diene system. See, 1, 2, 3, 4. 1 for cyclohexadiene. The conjugated alkene, upon Birch reduction, they are changed, they are converted into, diene is converted into an alkene. This is an example of alpha beta unsaturated compounds. So alpha beta unsaturated compounds, they also undergoes the Birch reduction and they are changed into ketones or substituted ketones. And last, the alkynes, I should rather draw alkynes like this. This is a terminal alkyne because the triple bond is present at the terminal carbon. So this is terminal alkyne. This is an internal alkyne. So terminal alkynes, they don't undergoes the Birch reduction, no reaction occurs. But the internal alkynes, they undergoes the Birch reduction into trans alkene. So what is the Birch reduction? Birch reduction involves the partial reduction of the aromatic system into diene system, conjugated diene system into an alkene. So the conjugated diene into an alkene, alpha beta unsaturated ketones into ketones, terminal alkynes into trans alkene. Now what is Birch reagent? Birch reagent. Birch utilizes the alkali metals such as lithium, sodium or potassium and dissolved it in liquid ammonia. You know, the ammonia is liquefied at minus 33 degrees Celsius. So it means that this reaction, Birch reaction, is carried out at very low temperature. So what happens when sodium, let's take sodium, is dissolved into liquid ammonia? What you get the blue color solution. You know, the sodium has very low ionization energy, so it loses its outer electron and that electron becomes solvated into the network of ammonia molecules. Since there are countless number of sodium atoms, so you get a pool of electrons solvated in liquid ammonia. So this network where pool of electron is solvated, is soluble inside the ammonia, so this whole solution color is blue color solution. So this reagent, sometime it is mixed with an alcohol, especially ethanol or methanol. So this reagent is utilized for the Birch reduction. You should memorize that how Birch reagent is prepared, and about the little bit history of the Birch reduction. And you also need to learn that what are the four different classes of the organic compounds that undergoes the Birch reduction, and what are the products that are obtained upon Birch reduction. We will study one by one in detail. Let's first discuss the reduction of aromatic compounds, and we will look into the mechanism in detail as well. Let's take a simple aromatic system that is known as benzene. I'm going to write now the reagent. Sodium and liquid ammonia. The reaction is minus 70 degrees Celsius. In the presence of protic solvent, protic polar solvent like ethanol. So benzene is converted into 1,4. This is benzene. This is 1,4 cyclohexadiene. 1,4 cyclohexadiene. So you see that only partial reduction has occurred. Now what is the mechanism? It involves set mechanism. What is set? Set stands for single electron transfer mechanism. Single electron transfer mechanism. As I have already explained, that the Birch reduction is actually the pool of electrons that are scattered inside the liquid ammonia solution. So what happens? So what happens? Sodium, it changes into sodium ion, plus also it evolves one electron. This electron attacks here, or it may attack here, here, at any of the carbon, because all carbon are identical so far. So electron, when one electron attacks here, you should notice that the what kind of arrow I have drawn here. I have drawn here a hook-like arrow. A hook-like arrow represents that the transfer of only one electron. So single electron transfer occurs. When this transfer, the electron attacks at this carbon, what happens that this double bond, it may delocalized over the entire ring. So what you get this single electron here, negative charge here, and this. And now this negative charge can easily be delocalized at carbon 1, 2, 3, 4, 5. Let's see how. When it comes between these two carbon atoms, then this bond will have to move over this carbon. So Also, when this negative charge comes here between these two carbon atoms, then this bond moves on this carbon. So you get another structure, one bond here, one here, and negative charge here. So you get three resonating structures. Among these three resonating structure, which resonating structure is more stable? You will see that this resonance structure, this canonical form, where this is electron, this is pair of electron, these are fully aparted from each other, they are fully separated from each other, while here or here they are closer to each other. So these two resonating structure are less stable and this resonance structure is more stable. So what happens next? No, uh, I will take this structure only because this is more predominant in concentration. What is the name of this? You should remember the name as well. This is benzene radical anion, and this is the most stable benzene radical anion. Then comes the part of this protic polar solvent, that is ethanol. What happens, this negatively charged carbon, it abstracts this hydrogen. So ethoxide leaves and it plucks this hydrogen and it is converted into, now what is the name of this species? This is 1,4 cyclohexadiene radical. 1,4, 1 2 3 4, 1,4 cyclohexadiene radical. Then again another electron attacks here and this radical is converted into fully negative charge. What happens next? This negatively charged carbon, it acts as a nucleophile and it abstracts this hydrogen, ethoxide leaves, and you get cyclohexadiene. The mechanism is very simple. I explain again for your better understanding, and this mechanism is very important to answer many questions. Later we will see that the sodium, it emits an electron. This electron, single electron transfer occurs at this carbon. This bond moves here, we get benzene radical anion, and this benzene radical anion has three resonance structures. The resonance structure, this is 1 2 3. The two resonating structure is more stable because the single electron and the pair of electron are quite far from each other. So what happens then? This negative charge, it plucks a hydrogen from a polar protic solvent. Then you get this. What is the name of this? This is 1,4-cyclohexene 1,4-cyclohexadiene radical. Then again the same step repeats. Single electron transfer occurs. Carbon gets negative charge now. Then it plucks or abstract the hydrogen from the polar protic solvent, and then it is converted into 1,4-cyclohexadiene. So partial reduction has now occurred. I am going to mark these two hydrogen with blue color because these two hydrogen have come from polar protic solvent, that was ethanol. Now let's study some examples that involves the substituted benzene. What is this? This is benzoic acid. And sodium and liquid ammonia is going to react in the presence of ethanol, and I'm going to write here the product. This product is obtained. Let's take another example. Using the same reagent, sodium, liquid ammonia in ethanol, we get this product. Now we are dealing with the substituted aromatic systems. The two substitutions were different. This is electron withdrawing group. It also has electron withdrawing inductive effect, and this it involves the electron donating group. What's the difference that you can observe here? This carbon that is directly attached to the substitution, this carbon is known as ipsocarbon. Ipsocarbon. This is another ipsocarbon. What you see that the ipsocarbon here is sp3 hybridized. sp3 hybridized. While the ipsocarbon, when electron donating group were present, this ipsocarbon is changed into sp2 hybridized. Now we will have to learn the reason. Let's first take this benzoic acid and draw the mechanism of this reaction. This electron, sodium, transfers single electron because this is a set mechanism. Single electron transfer mechanism is involved. Single electron attacks here, and this will move here. Now you should practice this many times. You should draw the resonating structures of this that is the cyclohexadiene radical anion. I'm now not going to explain. I will just write the resonance structure. We need to discuss these resonating structures a lot about. Here you can see that which resonating structure among these four is the most stable. Either this or this. These two resonating structures are very less stable because the electron and negative charge are quite close to each other. Among these two resonating structure, we see that this is the most stable resonating structure since they are quite apart from each other, and also the negative charge is on the highly electronegative element, that is oxygen. And here although they are quite far apart, but the negative charge is on carbon, which is comparatively less electronegative as compared to oxygen. So this, it will react further. I'm going to draw only this most stable resonating structure. Actually, in this medium where we are using the ammonia, which is a base, and carboxylic acids, they are quite acidic in nature. So what is going to happen, that this hydrogen is already present into the ammonia in the form of ammonium ion. So you'll have to write like this. So this resonating structure, which I told just quite a few seconds ago, that this resonating structure, because of these two negatively charged oxygen, they repel each other, so it becomes less stable. So which is the more stable among these four resonating structure? This one is more resonating structure. Okay. So we will have to take this one. This oxygen is, this resonating structure is more stable. So what happens next? The next step is very simple. This carbon or carbene ion, it plucks this hydrogen, ethoxide leaves, and you get hydrogen here. This hydrogen has now come from solvent, that is ethanol. And here we have a single electron. What happens next? Another set or single electron transfer occurs from sodium. You will get negative charge here and OH here. In the next step, is negatively charged carbanion, abstract hydrogen, and finally you get the product. What are you observing? That the ipso carbon is sp3 hybridized when electron withdrawing group was present. Now let's look into the mechanism of this aromatic system where electron donating group is present. Me is methyl, so I'm going to write CH3 instead of Me. What happened? Sodium releases an electron. Electron attacks here. Then radical anion is formed, and this radical anion has resonating structures. Let's draw. Now we have three resonance structures. Which resonance structure do you think is more stable? This resonating structure is quite unstable, that electron and negative charge are quite close to each other, the same like this. Here the two charges are quite far from each other, but what do you know, that this is an electron donating group. It will also try to donate a pair of electron into the conjugating system. So there is huge electrostatic repulsion between this pair of electron and this pair of electron. So this is quite unstable structure as well. So what happens here? The sodium has transferred a single electron at the para position. Now there is another option, that the sodium transfer its electron meta at the metacarbon. Then what will happen? That this negative charge will come here, we will get another radical anion. Let's draw its resonating structure. This bond will come here, and this bond will move here, and this carbon will get negative charge. If this negative charge comes here, then this carbon will get negative charge. Now we have drawn another three resonating structures. What do you think that which among these three, one, two, three, which is more stable? This resonance structure is not so stable as electron and pair of electron are quite close to each other. And also this second one, this is quite stable as compared to these two. Why? Electron and a pair of electron are quite apart from each other, and also there is no electrostatic repulsion between the lone pair of this oxygen and this negative charge, as we have already seen in the previous when we discussed the para attack. So here we discuss the meta attack. Para attack, attack at the para carbon. Here we have the meta attack, attack at the meta carbon. So what do you see? You see that when the electron donating group are present, then meta attack is more favorable, because in this we are getting stable resonating structure. So this will react further. What is the next step? Next step is quite simple, just to abstract the hydrogen from the solvent. It will attack here, ethoxide will leave, and this carbon will abstract this hydrogen. This hydrogen that has come from solvent, protopolar solvent. This is substituent, nothing is going to happen on this methoxide. What will happen next? Again, one sodium atom, the second sodium atom, it will transfer one electron to this carbon, so this will change into negative charge, because we know have a negative pair of electron. What will happen next? The abstraction of hydrogen. Now you have the product. These two hydrogen, let's mark them with blue color. These two hydrogen have come from protopolar solvent. The important thing to notice here is that the ipsocarbon, what is the hybridization of this ipsocarbon? It has sp2 hybridization. So you will have to remember this principle, that when the substituent is electron withdrawing, then this carbon will be sp3 hybridized. When this substituent is electron donating, then you will have sp2 hybridized carbon. Now what are common electron withdrawing groups? Those are carboxylic acid, amides, cyanides, nitro, and phenyl. These are common electron withdrawing groups. So if I write this reaction, you will have to tell me the product. Sodium and liquid ammonia. So in short I am writing the Birch reduction. We know that the Birch reduction will produce the diene system, and that diene would be this one. The ipsocarbon is sp3 hybridized because this was the electron withdrawing group. Now, what are the common electron donating group? These are ether, amine or substituted amine, thiol, phosphine, and etc. They have a lone pair that could be donated into the aromatic system. So in case of electron donating substituent, what will be the product? For example, if I have this, if I say you tell that what will be the product. So as I have already told you that from the mechanism that in case of electron donating group the meta attack is more favorable, and then when you will draw the mechanism you will see that your product will be this. Sodium in liquid ammonia in polar product solvent like ethanol. So this would be the major product where the meta attack is more favorable. What is the hybridization of this ipsocarbon? sp2 hybridized. Here you have sp3 hybridized. I hope you would remember this principle. Now let's discuss another aromatic system. What is the name of this compound? This is naphthalene, orthomethoxynaphthalene, or if the hydrogen would be here, then it would call naphthol. So you will see that we have the methoxynaphthalene. And here I take nitro group here. Now these are two different starting materials. We are going to perform Birch reduction. Which part of the ring will get oxidized? Remember that the electron withdrawing groups they lower the energy of the ring, and the deactivating ring they react rapidly with the Birch reagent. So in this case this ring will undergo the Birch reduction, and here which ring is more deactivating? This ring is very activating because the pair of electron could easily be involved in the conjugation. So this group, electron donating group, they are actually electron rich substituent. They activates this ring, and I have already explained that the deactivating ring reacts faster. So Birch reduction will occur at this site, at this part of the ring. But in this molecule, the Birch reduction would occur in this side of the ring. This is very important example and you'll have to remember this. So what are the products? Product will be these. If you will use only one equivalent of the Birch reagent, and here what will be the product? This ring will remain intact, and here this would be the product. So deactivating ring will undergo Birch reduction faster, quite rapidly. And if you have simple naphthalene, what will be the product of the Birch reduction? Let's draw its mechanism and try to understand. Let's take just naphthalene. Sodium will generate an electron. Electron will attack here. Now you'll have to draw the resonating structure of this radical anion, naphthalene radical anion. And when you will draw the resonating structure of this naphthalene radical anion, you will have to search which is the most stable radical anion, that is thermodynamically the most stable, and that will undergo the Birch reduction further, that will proceed further. Sorry. This will generate, so these are the different resonating structures of naphthalene radical anion. Now, dear students, you will have to understand that which resonating structure is the most stable among the six. You will see that here we have, sorry, a double one. You will see that those resonating structure are more stable that has benzenoid ring in them. Here electron and negative charge are quite closer to each other, so this is not so stable. 1 2 3 4 5 6, so one is not stable, so stable. This two, here the electron and negative charge are quite far from each other, and also they have benzenoid ring which is quite stable ring. So overall this two is very much stable. This resonating structure is not so stable, that electron and negative are quite close to each other. Here the electron and negative charge are very far from each other, but since you don't have benzenoid ring, the same is the case with this one. What about this 6? These two, 2 and 6 resonating structure, they have equal contribution, 50% this one, 50% this one. So these two resonating structure are most stable among these 6 resonating structure of naphthalene system. Here electron and a pair of electron are quite far from each other, and also one benzenoid ring is also present, so either this or this would undergoes reduction further. What will happen? Just the next step is quite simple. If you will judge that which resonating structure was most stable, hydrogen here, this carbene ion will abstract hydrogen from polar protic solvent. You will have now, what will happen next? Another set will occur. Set means single electron transfer. Negative charge. And it will pluck hydrogen from polar protic solvent, and it will change into this one. Whether the reaction will stop here or it will undergo further partial reduction, yes, it will undergo further partial reduction, because we can see this another aromatic ring is present. So students, I am just now drawing the final product of this reaction. You should draw its mechanism by yourself. You will have to use sodium, single electron transfer will occur, and you will have to find the most stable resonating structure that will proceed further for the abstraction of proton. Now this alkene would not react because this is not a conjugated alkene, so it will remain as it is, but this part of molecule will undergo reduction. So this is your final product. So if in exam, if I draw naphthalene and I say you to draw the final product of the Birch reduction of the naphthalene, then you will have to draw this structure. you will have to practice with anthracene as well. Anthracene, sodium in liquid ammonia in the presence of ethanol, what will be the product? You will have to try this by yourself. And I have already explained you that if in exam I ask you to compare the reactivity of these two starting compounds, and among these two which will react faster and what would be the product, you will have to understand, you will have to memorize that when the which part of the molecule is more deactivating and where there the uh, Birch reduction will take place. Here nitro group is present, so this ring is more deactivating. So what will happen, the Birch reduction will take place here, so that's why I have drawn here. You'll have to another you will have to notice that here the ipso carbon is sp3 hybridized. Why, I have already explained. When electron withdrawing group is present, then as the attack will be at the para position, and this carbon will undergo the Birch reduction here and here, so that's why you will get sp3 hybridized carbon. In case of electron donating, this ring is electron rich, so this part of molecule which is comparatively deactivating as compared to, so partial reduction, Birch reduction will occur here, and you will get this product. Again, dear students, this lecture is quite big, so I'm going to split the Birch reduction into two parts. So today we shall restrict our lecture to only this. uh, Next time we will study the Birch reduction in dienes, and these dienes must be conjugated to each other. So thank you so much.